In this lesson, we're going to discuss the difference between complete and incomplete combustion reactions. Both of these reactions usually involve burning a hydrocarbon, which is a chemical compound containing carbon and hydrogen. The fundamental difference between a complete and incomplete combustion is, do you burn your hydrocarbon with extra oxygen or with not enough oxygen? A complete combustion reaction always follows this pattern. You take something with C's and H's in it, you add some O2, and you only get carbon dioxide and water as your products. This is because we're burning our fuel source, our hydrocarbon, with extra oxygen. So all of the carbon in your fuel source becomes CO2, and all of your hydrogen in your fuel source becomes water. You can recognize a complete combustion by looking at the color of the flame. It's a very clean burn, and you get blue or white flames coming out of your reaction. As human beings, we like to have complete combustion reactions for a couple of reasons. First being that it releases the maximum amount of heat from our fuel source, and then we can use that heat to do work, like heating our homes, cooking food, and pushing pistons to work engines. We also like complete combustions better because they're actually a lot safer, because they only make CO2 and water as our products. Now, usually when we do complete combustions, we're using a hydrocarbon as a fuel, but we can use individual pure element samples and do complete combustions with them as well. When you look at reactions like this, you will first see them as a synthesis reaction, but anytime you take some kind of fuel and burn it in oxygen and create the most stable oxide for that element, it can be double classified as both a synthesis and a complete combustion. For example, if you take magnesium and burn it as a fuel with some oxygen, you can make some magnesium oxide. And with your previous chemistry experience, you guys will remember when you do this reaction, it gives you a very white, hot flame. That's one of the signs of a complete combustion. Most people look at this and say, hey, it's a synthesis. I've got two becoming one. And we've got this special pattern. If I have a metal plus oxygen, gives me a metal oxide for our synthesis patterns. So classifying as a synthesis reaction makes sense, but it also fits the criteria for a combustion. So some reactions we can actually double classify, and this is one of the examples. If you call it a synthesis, I will always take it as being correct, but understand that you could also call this a combustion reaction. Incomplete combustion reactions follow the same pattern, except that you limit the amount of oxygen. You don't add enough to your fuel mixture, and so you run out of it as your fuel burns. You recognize these ones because you make up to 4 different products. Here we've got a couple of examples of burning octane, which is the main ingredient in gasoline. If you burn some C8H18, which will be our hydrocarbon fuel source, with a little bit of oxygen, you're going to see some CO2, some water being made. But as you start running out of oxygen, there won't be enough oxygens to stick 2 on the carbon. And so 1 will start detaching, and you'll make some carbon monoxide. When you totally lose out on all of the oxygen in your reaction container, then you'll get some solid carbon made. This solid carbon often comes out as soot, ash, or smoke. So incomplete combustions are generally described as dirty burns. You recognize these by seeing a yellow or an orange flame. Now, the exact composition of your products will change depending on how much oxygen you add in. The less oxygen you add to your burn, the more solid carbon that comes out. And the more oxygen that you burn, you'll get more CO and maybe a little bit more CO2. So really it depends on the real life situation of the amounts that you mix your fuel and your oxygen together. Now we'll get into our discussion about mixing in different chemical amounts in Unit 3 and predicting the amounts of product that gets made. So until we learn those calculations in Unit 2, when you write an incomplete combustion, what I want you to do is write down all 4 products. So you're going to take your fuel, add some oxygen, and you're going to write down CO2, H2O, CO, and solid C if I asked you to write an incomplete combustion. Now, when you're balancing the equation, there's more than one possible answer. It all depends in real life how much pure oxygen you mix in with your fuel source. So when you're writing balanced chemical equations for these, just show all 4 products and show one possible answer. So here's another example of showing the incomplete combustion of octane. Notice in this equation I've just added some more oxygens than I did in my first example. And you'll notice when I balanced it, it came out, I get more CO2 than solid C coming out of my reaction. Both of these balanced chemical equations would be acceptable for showing the incomplete combustion, and there's actually more. All you have to do is get it balanced somehow, and as long as it's balanced, I'll take it as being correct. We'll deal with mixing in chemicals in certain amounts in our next unit, so we'll come back to this conversation then. One thing to notice when you're doing your states is that both in incomplete and complete combustion reactions, the water comes out as a gas. That's because these kinds of reactions release a lot of heat, and you get steam coming out of them instead of liquid water. You might have been getting into the habit of always putting water as being liquid state. Remember, that's if it's at room temperature. And combustion reactions don't happen at room temperature usually. So make sure you do that switch whenever you're writing a combustion reaction, whether it be complete or incomplete, to put the state of water as being a gas. Now, as human beings, we're constantly trying to avoid incomplete combustion reactions and engineering things to make sure that every time we burn something, it's as complete as we can get it. Now, this is for a number of reasons. The first being that incomplete combustions are dangerous. When you make carbon monoxide, it's a poisonous, tasteless, odorless, colorless gas, which is fatal to humans. And this is why you need to have a CO detector in your house, because often we have appliances in our homes like furnaces and water heaters, and some people have gas stoves that can build up CO in your house and potentially kill you. This is why it's also recommended, like every fall before you flip that furnace on in your house, you get a certified technician to come in, do a cleaning and a service, and they will test to see whether or not your furnace is burning completely or incompletely, and if it's running safe or not. This is also why some appliances like barbecues, fire tables, gas patio heaters are for outdoor use only. As a barbecue gets used, its gas jets can get gummed up by grease and oils and things like that coming off your food, and that might actually cause an incomplete combustion, which is why you always have to use these appliances outside and never inside in the garage. Every year in the wintertime, if there's a power outage, you hear news stories about some family who's passed away or have gotten CO poisoning and are really sick because they don't have any heat for their house. So they bring in a barbecue or they bring in an outdoor patio heater and unfortunately use it inside, and that gives them the CO poisoning. The second reason why we want to avoid incomplete combustions is because we don't get the maximum amount of heat out of our fuel source, which means it's less efficient. So if your furnace is burning incompletely, then you're going to be burning more gas and getting less heat out of it, which is going to increase your gas bill. For practice, try out these homework questions. For question 1, write balanced chemical equations, including states, for the complete combustion of the following fuels. and it'll tell you what state each fuel is in the question. For question 2, write balanced chemical equations including states for the incomplete combustion of the following fuels. Sorry, looks like there's a typo on your note there. Again, it's got the state of each of these fuels in the question, so you know what state to put in your equation.